Okay, so let's look at this puzzle. So the puzzle is talking about Susan, who is 28 years old. She is bright, outspoken, single, major in philosophy, concerned with discrimination, social justice, participated in anti-nuclear demonstrations. She's a cool kind of person. So what do you think out of the following statements is more likely and less likely? Can she be an active feminist, a bank teller, an insurance salesperson? What do you think? Probably when you looked at those options, you thought, well, somebody like that is very likely to be a feminist. Insurance salesperson, not nearly as likely. But now let's just look at two of those lines. Among the number 6 and the number 8, which one did you say was more likely? Is she more likely to be a bank teller, or is she more likely to be a bank teller and an active feminist? If you show this puzzle to your friends and relatives, there is a great chance that they say, oh yeah, being a bank teller and an active feminist is a lot more likely because she's more likely to be a feminist and a bank teller. But let's think logically about it for a moment. If we look at all the people who are bank tellers and we look at all the people that are feminists, some people would be in both of those groups. Some people would be in just one group but not the other. But no matter what those groups are, the number of people who belong to both groups is always going to be no more than the number of people who belong to one of the groups. In particular, feminist bank tellers are more rare than bank tellers because in order to be a feminist bank teller, first of all, you need to be a bank teller. And there are bank tellers that are not feminists. So even when you're reading it, you may think that a bank teller and an active feminist is a more likely option. It's actually less likely, just for the reason of logic. And it really has nothing to do with whether it's bank teller, feminist, or some other labels. It's always less likely to be part of two groups than just one of them, or at least it's no more likely. So this is the kind of logic that we want to talk about in the next few lectures. The logic that talks not just about propositions, is it snowing today, is it not snowing today, but about something more realistic, scenarios involving people and numbers and birds and trees and computer program, all sorts of other things. We want to be able to extend our reasoning from propositional to what we will call the predicate reasoning. And this is one example of that. So before we start talking about logic, we first need to talk about what we are going to be reasoning about. And the central notion there is the notion of set. So a set is that's one of those words that kind of has a definition, but the definition almost says the same thing as the word itself. So a set is just a collection of objects. You could have a set of houses, a set of numbers, a set of people, a set of animals, or actually a set of pairs of animals, or a set of words. And we will be talking about some properties of those objects. And now we will be talking about things that are true or false. Is a given number divisible by 4? Is it greater than 10? Is this person a bank teller? Is this person a feminist? So here our scenarios will correspond to objects, and our logic will be about properties of those objects. So in a set, we just look at object in no particular order. The only thing really that we would want to know about a set is whether something belongs to that set or it doesn't, whether something is a house or not, whether something is in a set of numbers 1 to 3, well, if it's either a 1 or a 2 or a 3, then it is. If it's anything else, a number or not a number, it's not. We could talk about sets of people. When we write down sets, if we have very few things to describe, we can just list them between the curly brackets. So we use curly brackets to differentiate it from other notation that we will use later on. We will be talking about sequences of things where the order will matter. So when you see curly brackets, you could rearrange things inside of them. So Cassie, Alla, Keika, Daniela, maybe want to say Alla, Cassie, Daniela, Keika, and that will be exactly the same set. A lot of times we will be talking about sets that are much bigger than 1, 2, 3. And in this case, rather than describing them by listing all the elements, we will use a set builder notation, which says that set consists of all elements, usually from some bigger set, that satisfy some additional property. For example, you could talk about a set of all even numbers, of all people on Earth right now, of all bank tellers, of all houses. And again, in order to belong to the set, an object should satisfy this property. For example, it should be a person who is a bank teller, or it should be a house. And if an object doesn't satisfy the property, it would not belong to the set. Here are some special sets that you probably have seen before, but we will be using a lot in this course just as shortcuts, just to save us space in writing. One of them is an empty set. That's the special set that contains nothing at all. There are no elements in it. No matter what you pick, a number or a house, it does not belong to the empty set. And we write it as a crossed 0 or cross O. Another set is natural numbers, which are the very first numbers that people started talking about. Usually, although not always, the natural numbers are numbers 1, 2, 3, 4, and so on. Sometimes, especially in computer science, you see them starting with 0. It's just like counting floors of the house. In some countries, your ground floor will be number 1. In some countries, your ground floor will be number 0. In some countries, your ground floor will be called ground floor, and the floor number 1 will be above it. Same with natural numbers. For integers, there is no such controversy. Integers are natural numbers, negated natural numbers, or zeros. So -2, -1. Sometimes people call them whole numbers. Rational numbers are the numbers that can be represented as one integer divided by another non-zero integer. And here we have things like 2/3, 15/4, and so on and so forth. All the integers are also real number, because you could write number -1 as -1 divided by 1. In fact, you could write any integer as that integer divided by 1. And the Q symbol comes from the quotient. After integers, we have real numbers. You might have heard about the number line. That's usually real numbers, which are just sequences of digits. And also in computer science, a very, very prominent set is called binary strings. So in computer memory, things are represented in binary using on and off, power or no power, 0 and 1. And the sequences of those zeros and ones encode everything. So binary strings, which are finite sequences of zeros and 1, they are very, very common in all sorts of areas in computer science. So for example, the string 001 will be in the set of binary string. There is also a special string which has no characters. But all the strings in binary consist of only zeros and ones, and all the strings in binary are finite. So we will use the notation A in S to mean that a certain element belongs to a set. So an element A belongs to a set S. And we will cross that in symbol to mean that it doesn't belong to the set. So if you think about it as a logical formula, as a proposition, looking ahead to doing logic with sets, A in S is true, has a value true, if the element A is indeed in the set S. For example, Susan is a person, so Susan is in the set of people. Susan is not in a set of bank tellers. Well, that may be true, that may be not true. We don't know. 0.5 is a real number. It's actually even a rational number. However, 0.5 is not an integer and not a natural number. In addition to writing A in S for a specific element, we will very often write X in S for some variable that we will call X or Y or Z or some other variable name. And this is very useful in particular for the set building notation, where now we could just say not just X such that X is a person and is a bank teller, but X from the set of people that in addition satisfy a property of being a bank teller, or X is an integer which is additionally divisible by 2. That will give us our set of all even integers, positive or negative. So one more thing is the relationship between different sets. We want to be able to say that sets are equal or not equal, and we want to say how elements of one set relate to elements of the other set. Again, think about our example of people, some of which are bank tellers, some of which are feminists, some of which are both. For that, we will use the notion of subset. And the subset just means that all the elements of your set, which is a subset, belong to your bigger set. For example, the set of all bank tellers is a subset of the set of all people. The set of even numbers is a subset of all integers. Natural numbers as well are subset of all integers. Moreover, they're subset of all integers greater than or equal to 1. And we can define what it means for two sets to be equal by just saying, well, the two sets are equal if they contain the same element, because really the only thing we could say about a set is does it have an element or does it not have an element. So for example, natural numbers and all integers greater than or equal to 1, that's the same, because every number, if it's natural, it's an integer greater than or equal to 1. And if it's an integer greater than or equal to 1, then it's a natural number. That's kind of how we define those things. So how do we say it when two sets are not equal, but still one is a subset of the other? We will call it a proper subset. For example, bank tellers is a proper subset of all people because some people are not bank tellers. Even numbers is a proper subset of integers because some integers are odd. And we will use the notation with additional little line when we allow the possibility when the two sets are equal, and without it, just the subset symbol when we want to say it's a proper subset. So not only all elements of S1 are in S2, but additionally there is at least something in S2 which is not in S1. So now that we defined sets and we talked about the grand picture of general scenarios involving people and numbers and animals, how do we actually do logic with sets?